Welcome back. This is a Tutor Wizard. I'm Adrian. This is Ringo. This is Alice. Please subscribe right here. Hit the notification bell. This time what we're doing is Linear Algebra 1. We're doing Chapter 3, which is Geometric Vectors, Lines, and Planes. Section 3.5 is going to be dot product and cross product. Last time we did the dot product explicitly. This time we're going to do the cross product and some examples. I know, it's exciting. Let's get to it. All right, let's get to it. Definition. Let U and V be vectors in R3. I'm going to remind you that cross product only works in 3 dimensions. And we're always going to, and you should be happy because we now have coordinates for vectors. So they're going to have 3 coordinates. There's going to be an ambient basis, usually the canonical basis I, J, K. Those vectors are already written, so they have as a linear combination of those basis vectors. So they have 3 coordinates, U1, U2, U3, V1, V2, V3. Our original definition, those are not going to appear anywhere. One of the goals of this video is to give ourselves coordinates of the cross product based on the coordinates of U and V. This will be one of our major theorems on how to compute this thing. What is the actual definition though? The cross product of U and V in R3 is a vector W, which we're going to denote U cross V. Satisfying these 3 conditions is what we want. These arrive from a bunch of scenarios in physics again, and what we're going to do in the next scene is we're going to give you one of those angular momentum derivations to see where this comes from or why they would want these 3 conditions. What are the 3 conditions? The 3 conditions are cross product, the length of that vector, whichever we're creating. The length of that vector should be exactly the area of the parallelogram determined by those 2 vectors. The other thing we should have is we want it to be perpendicular to both of those vectors laying in that plane they're in. So they're in some plane. We want a vector standing perpendicular to the plane, in particular to both of those vectors. And this is our symbol. So W should be perpendicular to U and W should be perpendicular to V. And then the last thing from more physics type of thing that we want is the right-hand rule. This is what they're talking about, counterclockwise. So U and V and W form a right-hand triple of vectors, which means as seen from the endpoint of the vector W, the shortest way to move U to V is counterclockwise, this way. This is the right-hand rule. I physically can't go this direction, but I can go this way. This is counterclockwise, and if this is U, this is V, this is W. As seen from W, the shortest way to move U into V is counterclockwise. These are the 3 conditions I want for this. And specifically, you can see it's not hard to derive the fact that the area of the parallelogram is norm of U times norm of V times sine theta. Why is that? Well, you have to remember some area formulas. The area of a parallelogram is base times height. In this picture, the base is the length, the magnitude of the vector U. And the height from trigonometry is sine theta is opposite over hypotenuse. So we can solve for H. H is exactly norm of V sine theta. Therefore, area is base times height, which is norm of U, norm of V sine theta. So this is the guy that we're looking for specifically. Let's now give a derivation for angular momentum and where this would come from in the real world, or why I care about the cross product at all, because I said so. Again, before I move on with all the properties and some examples, let's give a motivating derivation for where cross product comes from. We have linear momentum and angular momentum. In angular momentum, we have a particle with mass m moving in the plane. It's moving along a curve gamma, and then it has a linear momentum mv, and it has position vector r, which is OA in our diagram. You don't have to worry about this, this is the derivation. Then what we're looking for specifically is the angular momentum of this particle about another point O. So we have this point here, it's moving along, that's our mass, and it's moving along a curve. We want to know what its angular momentum is about this point. So to show that, what we're going to show is that it's basically the cross product of the position vector r and the linear momentum mv. How are we going to see that? We need 3 things, the 3 conditions in our definition of cross product. So the first thing we have is, because the particle is moving in the plane, we can fix the position or the direction of L to be perpendicular to this plane. By fixing L coming out of the plane convention only, we're going to have it come up from the plane, not down. It could be either one, but by convention I'm going to do this. Why? Because it gives us 2 things. First of all, because we're saying it's perpendicular to plane, it's perpendicular to the vectors in the plane, so it's perpendicular to R, and it's perpendicular to MV. That was the condition 2. The first condition was that it's the area of the parallelogram, which we're going to get to in a second, and condition 3 actually was the right-hand rule. If we make it point up now, you'll see that as viewed from L, the closest way to rotate this one into that one is going to be counterclockwise. So what's the last condition I need? I need the first condition of this definition, that the magnitude of L is in fact the magnitude of R times the magnitude of mv, the linear momentum, times sine theta. Why is that? We look at another picture where L is now pointing out specifically from the board. And what we're going to do is we're going to decompose the linear momentum into its two components. We have mv parallel to the motion and perpendicular to the motion. What is the magnitude of that perpendicular one? This is the one that's involved in the angular momentum. The parallel one is going to be whether you're moving inwards or outwards towards that, not angularly around the point. Using trigonometry again, it's going to be sine theta is opposite over hypotenuse. Solving for this here, we're going to get specifically that the magnitude of mv perp is the magnitude of mv times sine theta, cleverly. Therefore, the magnitude of the angular momentum is going to be the product of the magnitude of the position vector and the magnitude of the perpendicular component. What is that? The magnitude of R is itself. The magnitude of mv perp we found to be the magnitude of mv times sine theta. Long story short, what is that doing for us? The whole point is, what is this guy by definition? That is going to be the magnitude of the vector R cross product with the vector mv. Therefore, the angular momentum, L, is going to be viewed as the cross product of the position vector and the linear momentum, mv. So this is one of the motivations as to where in physics the notion of cross product comes from, angular momentum. Other places it comes from is when we do torque, which is also rotational force. So there's going to be cross product there. And then the Lorentz force, which is basically particles moving in a force field. There's also is a derivation of the cross product. So this comes from, I'm trying to understand the universe, not just trying to torture first year students. This is always a good application, but not for motivational reasons. Let's do the theorem, which actually gives us the coordinates of cross product. All right, before we give the coordinates specifically, let's look at theorem, which is the properties of cross product. We have properties of dot product. Now we have properties of cross product. First of all, it says now I put the U, or the important one, which is why I want the rule, in pink. So if the order now specifically matters in dot product, U dot V is V dot U. It doesn't matter if you flip them. You don't have to pay attention. This time you do. When we just derived this, L, we even said we can have L pointing up or L pointing down from the plane when we do this. So this is going to be negative L, and they're both cross products. So if you switch the order U cross V, in magnitude it'll be the same, but you get a negative, you get the vector pointing the other direction perpendicular from the plane. What number 2 says is cross product distributes over sum of two geometric vectors. In particular, notice that it says that it's going to be U cross V plus U cross W. The third one tells you, once you see how we compute this, and we do this in the last scene, you're going to see that computing U cross V is not super easy at first, or once we give it as a 3x3 determinant, you have to practice determinants, but it's okay. But if you notice that there's a 7 out front, don't put the 7 in the determinant and compute. Pull the 7 out, compute the determinant, and then multiply the number by this vector that we create. In the fourth one for dot product is U dot U is the norm of U squared. In this one, U cross U is always the zero vector. It makes things disappear. Anytime, I'm going to do an example right now, and anytime I get U cross product with itself, I get the zero vector and then it disappears in the equation. So let's do one example of how I would use these properties. These are the only rules you're allowed to use when you're trying to manipulate. You can't see right now where you would get an example where I would need to manipulate and do that, so let's do one right now. All right, example 1, find the area of the triangle, not the parallelogram, but this is all of a sudden, it's like, yeah, I'll take care of you just a second, but find the area of the triangle formed by the vectors 3U plus V and U minus V. If all we know is, see, we haven't given you coordinates, so what Mark cleverly likes to do is come up with problems where you have to use the definition of the cross product and not have the coordinates to do the problem anyways, and use the theorem where we use the properties, and that's what's going to happen. So all it gives us is the magnitude of U is 1, it's a unit vector, the magnitude of V is 3, and the angle between them, all crash course in trigonometry, what's sine of 30 degrees? That's right, 1/2. Our angle is going to be 30 degrees specifically, and from this apparently you have to realize how to set this up and figure out what the heck is going on here and use the theorem and the definition of cross product to compute the area of this triangle. Please do what I almost forgot to do, and Mark would probably email and yell at me because I didn't put it in the video. What's the first thing I should be doing here? Draw a picture. Then it's not all this abstract mumbo jumbo. So what they mean, first of all, is, and where we get the connection is, we have U right here and then V right here. And then we say that is the parallelogram determined by U and V, or formed by the vectors U and V. We're going to do it for some other vectors, 3U plus V. We're going to dilate U by 3 and then add it to V and then take their difference, and those vectors are going to create some other parallelogram. So we're going to be doing this guy. That's what we're looking for. Except now it said the triangle. Well, luckily the triangle is half of parallelogram. We know that the area of the parallelogram, determined by U and V, which I will use as syncopated algebra, we'll use some pictures and some algebraic formulas. The area of that whole parallelogram is equal to the, in general, I wanted to go back to confuse myself when I just have two U and V. This is probably what's confusing you also. So if I just have two vectors, whatever they're called, A and B, or U and V, then the area of that, the entire object is equal to the norm of U cross V. And so what we want is the area of the triangle determined by U and V is going to be 1/2 of the norm of U cross V. And that's in general the definition. And now this is what also is probably possibly confusing. Now I have to replace U and V with the vectors 3U plus V and U minus V. So what is that going to look like? Well, let's just rewind that. This is now going to be 3U plus V. This is going to be U minus V. So what does that tell us? This area now that I'm looking for my picture is going to be A is going to be 1/2 times the norm of 3U plus V cross product with U minus V. Because those are the two vectors they gave us that determine the sides of that triangle. And this is what we're getting at. Now, I'm not going to start with that. What I'm going to do is use the norm at the end. But first of all, let's unwind just that cross product with all the machinery, and this is where the theorem comes in. I want to look at 3U cross V, or sorry, 3U plus V cross product with U minus V. First of all, from our theorem, what that tells me is I'm allowed to distribute this thing onto both of them. So what I'm doing is viewing this as, I know it's weird at first and that's not the clever move, but the key to ingenuity is hiding your sources. Steal it from me then. Well, I'm going to view that as a single vector W, and now I'm going to distribute that onto these two vectors using that property. So what does that give me? That will give me 3U cross V. I keep wanting that to be a cross. 3U plus V cross product U. And then plus, I'll take care of the negative in a second, 3U plus V cross product with negative V. And that's like a negative K. That's a K, so I could move that negative to the front if I want, or all kinds of business. We'll leave it for now. Now what am I doing? Technically speaking, I could introduce a negative by swapping them, or I can use the theorem and essentially I'm going to distribute it the other way, which you're also allowed to do. But this is going to give me 3U cross U. From the theorem, that's a K. Yeah, and I can move that out. You'll see why we're going to do that in a second. Plus V cross U. And then in this term, I'm going to do the same thing. I'm going to get plus 3U cross negative V. And then plus V cross negative V. Now I'm going to use the property 3. I can move the scalar out. I can move the scalar out. I can move the scalar out. This gives me 3 times U cross U, 0 by property 4, plus, careful, order matters, V cross U, minus 3 times U cross V, and then this one is minus V cross V. Why is that nice? Because these two go away. This is the 0 vector, and this is also the 0 vector, and everyone says, how did you make those terms go away? This is property 4. Anytime you cross product a vector with itself, you get the 0 vector. Those two terms are gone. Now what do we get? I'm going to move these ones around, and I can either make this one positive or that one negative. It doesn't matter. I like u cross v, so we're going to flip that one around. So what does that tell me? That is going to be negative u cross v minus 3 more of them. That's going to give me negative 4 u cross v. All right, now that we've got this guy, this is what that hot mess was. So now let's compute the norm of it. Therefore, what do we get? This tells me that the norm of 3u plus v cross u minus v is equal to the norm of negative 4u cross v, which is now I'm using a property of magnitude. And when you have a number, you can take the number out in absolute value. So this is going to be equal to the absolute value of negative 4 times the norm of u cross v, which is 4 times the norm of u cross v. I know I didn't forget the 1/2, just a second. I'll recap and remember what they were asking after I do all of these moves. Now, use the definition of cross product. The magnitude of that cross product should be the norm of u times the norm of v times sine of the angle between them, and this is why he's given us exactly this. These three things have to get used, otherwise they're red herrings in the problem. They're not red herrings, they're blue herrings, and we're going to use them all right now. What does that say? We have 4 times, it should be the magnitude of u times the magnitude of v times sine of the angle between them, which is 30 degrees. I don't even like 30 degrees. I shouldn't give those to you. Where we're going, we don't need degrees. It's always radians. 30 degrees is pi over 6 radians. What is that going to be? This is going to now give me 4 times, I can put that in there, 1 times 3 times sine of the angle between them. Again, we got these 3 major ones in the first quadrant. If you didn't remember, you're like, this is linear algebra. It doesn't matter. We're going to use math. Whenever I need some kind of thing in math, I use it wherever I want. This is pi over 6. This is pi over 4. And this is pi over 3. This one tells me, the way I always remember this is sine of pi over 6 is 1/2. That fixes everybody else. I'm going to get root 3 over 2, 1/2. We're going to get 1 over root 2, 1 over root 2. You can't see it, but go look at the unit circle or my videos on trigonometry of right triangles. And then this one is going to be 1/2 root 3 over 2. Those are usually the values I'm going to give you, but you can also use reference angle and the cast rule if you really need to find the exact values of arbitrary large angles. But in there, I know that this is going to be 1/2, long story short, sine of pi over 6 is 1/2, and that is going to give me 6 units squared. But that's not exactly what they wanted. Our area is 1/2 of that, the norm of 3u plus v cross u minus v, which is going to be 1/2 times 6, which is 3. This is how we compute. I used 3 major moves. I used the definition of the norm of cross product is the norm of u times norm of v times sine of the angle between them. I use the theorem, which tells us the properties of how to use cross product in algebra, the ways that we can manipulate them. And I've used and squeezed in there the fact that we know that the area of a parallelogram is exactly the norm of the magnitude of the cross product of the vectors determining them. Then the area of the triangle is just going to be 1/2 of that. Now let's do the actual, notice this example, I didn't need the coordinates of an ambient basis of 3 space or anything like this. I don't have the coordinates of the cross product yet. Now we're going to do that and view it as the coordinates of cross product is going to be a 3×3 determinant. Magic. All right, how do we get the coordinates for cross product? We know that one of the ways of doing it is we can just solve a system of equations, which I'll do, and then this isn't very efficient. These are what you have to memorize. This is how you compute cross product given the coordinates of 2 vectors. It's like, I don't want to memorize that. I want a clever formula. We're going to turn this whole hot mess into a 3×3 determinant and using cofactor expansion to do this. So from this scenario, what we know is u cross v is perpendicular to u and v. This should be a Pavlovian reflex by now. If u and v have coordinates in some canonical basis, I, j, k, then they have 3 coordinates each. Then we know that we're looking for some cross product and we don't know what the coordinates are. And this is what we're trying to say. What are the coordinates of this guy dependent on the coordinates of the original 2 vectors u and v? We do know that these guys are perpendicular, so that means their dot product is 0, and this is how I compute dot product. So I get a system of 2 equations and 2 unknowns. It's homogeneous. The right-hand side is 0. cleverly taking this now to find out what W1 and W2 are, and then we'll do W3 in a second, but to find out what those two values specifically are, we cleverly multiply equation 1 by V3 and equation 2 by U3, and it gives us these two equations. Then what I do is subtract, and I can kill off the W3 term for now, and that gives me this statement. Or if I move one to the other side, I want to know when these things are equal. The easiest way to do that is make them opposite to each other. I'm going to make W1 equal to this thing, and I'm going to let negative W2 equal this thing, and then we have a way of solving for W1 is going to be U2 V3 minus V2 U3, and W2 is going to be the negative of U1 V3 minus V1 U3. So for W, instead of deriving it again, basically instead of multiplying by V3 and U3, I multiply by V1 and U1, and then I would eliminate one of the other coordinates, and then I'll get a system which allows me to look at W2 and W3, say, and then I can find out what W3 is, also doing that clever trick again, and lo and behold, we have the coordinates of cross product. But this is the way that physicists are going to do it. We want, as mathematicians, we want a clever way of computing this, and you're going to agree with me, because then you'll have a 3x3 determinant, and that will be how we compute cross products all along. Let's do that. The moral of the story is we were looking for the coordinates of U cross V, which we call W1, W2, W3. We found those solving a linear system, which pleases me thoroughly, and then we got from that a hot mass of coordinates. Now every time I say compute U cross V, you have to remember that the first coordinate is U2 V3 minus U3 V2. How are you going to do that? I don't want to memorize this. I'm going to view this as cofactor expansion along the top row of a 3x3 determinant, where the top row is I, J, K, our canonical basis vectors. How are we going to see this? Let's unwind this from the reverse of the properties of scalar multiplication and addition of vectors and the definition of 2x2 determinants, and we're magically just going to have a 3x3 determinant fall out of this. How do we do that? This one, first of all, is equal to, using in reverse, this coordinate 0, 0 plus 0, this coordinate 0 plus 0, 0, this coordinate. I'm seeing this, I'm going to split it as the sum of three vectors cleverly first. What are those vectors? I see that this is U2 V3 minus U3 V2 0, 0 plus 0 negative U1 V3 minus U3 V1 0 plus 0, 0 U1 V2 minus U2 V1. I've just done the reverse of the definition of adding vectors once we have coordinates. I've pulled them apart, now I have three vectors. Now, because 0 times this thing could be there, I know that this is in all three coordinates, so I'm factoring it out of each one. This is going to give me U2 V3 minus U3 V2 times 1, 0, 0. Oh, that should be hitting a nerve by now too, plus the negative, or negative 1 times U1 V3 minus U3 V1 times 0, 1, 0, and then plus U1 V2 minus U2 V1 times 0, 0, 1. Now we'll do two moves. This vector is called I, this vector is J, and this vector is K, and then you need to see what these are. These are 2x2 determinants, AD minus BC. I'll write that out cleverly for you. This is a 2x2 determinant, U2, U3, V2, V3 times I minus the 2x2 determinant, U1, U3, V1, V3 times J, and then plus this 2x2 determinant, which is U1, U2, V1, V2 times K. And that, by definition, if you look, it's plus minus plus. That is cofactor expansion along the top row if we view this as a 3x3 determinant with I, J, and K in the top row. U1, U2, U3, V1, V2, V3. This is U cross V. And this is how we're going to compute, in general, the cross product. We're not going to try and memorize this from physics. We're going to use the fact that it's a 3x3 determinant, use some of our mathematical machinery, and compute a cross product as you put ijk in the top row, you put u in the second row and v in the third row. What happens if you put v in the second row and u in the second row? By interchanging two rows or columns, you get a negative in the determinant, and therefore u cross v is negative v cross u, so it won't matter up to absolute value, you get the same guy. They'll have slightly different negatives of the coordinates, but it'll be the same calculation up to the sign of the coordinates. Let's do an example of that, and then we'll do one more result. I know you're almost done, but we need to do the three-dimensional analog of what's the area of a parallelogram, the norm of u cross v, what's the volume of the word of the day, the parallelopiped. The parallelopiped is the three-dimensional object where it's a box, but it's been pushed on the side so the angles aren't 90 degrees, but then you have some box in 3 dimensions. One of these guys. This is a parallelopiped. And what is the volume of the parallelopiped? The volume of the parallelopiped is going to be the scalar triple product. Is going to have a dot product and a cross product. Let's get to that. All right, this is what you were waiting for essentially. Given the coordinates of two vectors in 3 space, what is their cross product? You will see in the next section when we do equations of lines and planes, we're going to need this specifically to find the normal form and the general form of the equation of a plane. We're going to need cross product. The normal vector is perpendicular to the whole plane and therefore the two vectors in the plane, so we're going to have to compute this all the time. What is the cross product of u and v? Well, if I use the one definition, I have to use this, and you're like, this is why. I'll point out this is what you would have to do if you don't know that it's a 3x3 determinant. This by definition is, and then when you're on an exam and you don't have any formula sheets, this is going to be what? It's u2v3 minus, I don't want to do it that way. So instead of having to memorize that, I'm not going to memorize it. What I memorize is how to compute 3x3 determinants, and cleverly it's this. It is I, j, k, and then I put u in the first row, or in the second row, 2, 1, 1, and I put v in the third row, 1, 0, negative 1. Now I cofactor expand along the top row, and this gives me, what do I get? I'm going to get, blocking this off, I'm going to get 1, 1, 0, negative 1 times I minus 2, 1, 1, negative 1 times j plus the determinant of 2, 1, 1, 0 times k. If you don't remember how to do this, go back to section 2.4.1 and watch the video on how to compute determinants by cofactor expansion. This is going to equal, what do I get? I get negative 1i minus, let's be careful, I'm going to get negative 2 minus 1 is negative 3j, and then plus, what do I get? Negative 1k, which is negative I plus 3j minus k. And then here's where everybody says, and then I write it like this, and everyone loses their mind. Because remember, this is equal to, I'll do it once because we're in the tutorial video, but you should memorize this. I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. So this is negative 1 times 1, 0, 0 plus 3 times 0, 1, 0 plus negative 1 times 0, 0, 1. I use scalar multiplication, scalar multiplication, scalar multiplication, and then I add those vectors, and I'm going to get negative 1, 3, negative 1. We did all that work. Oh, on a test there's a check. Let's check, did we do it right? Do you believe me? What is the check? This is a good connection. Also, how we derived the coordinates originally before I found out that it was a 3x3 determinant was we use the definition of dot product. It has to be orthogonal to both of them. So compute this. We know that u cross v has to be perpendicular to u, and u cross v has to be perpendicular to v. So check at least one of them and you should be good to go if you get 0. That's if and only if the dot product is 0. So what do I get? U cross v dot product now with u is going to be what? Well, u cross v was negative 1, 3, negative 1. Dot product with 2, 1, 1, which is going to give me negative 1 times 2 plus 3 times 1 plus negative 1 times 1, which is negative 3 plus 3, which is 0. Oh, it's orthogonal, so it gives us a check. If you really want, you can check that u cross v is also perpendicular to v. Now let's wrap this video up by doing how to compute volumes of parallelopipeds in 3 space. So one more definition and one more result. The definition is going to give us a way of computing volumes of parallelopipeds. Definition, let u and v and w be vectors in 3 space. Then the scalar triple product, this is one of the rare cases of a trinary operation. I'm going to take three things and compute something else from them. In this case, I'm going to take three vectors in three space and compute a number from them. That number, I know in symbols it all looks Greek to you right now, but this is a real number, and that real number is going to represent the volume of the parallelepiped determined by u and v and w in a second, but it's a number. So u dot v cross w is going to be the scalar triple product of u and v and w. Note that v cross w creates a vector. It's a vector operation. So given two vectors v and w, it creates another vector v cross w. And then when I take that vector and dot product with another vector u, that's going to create a real number or a scalar. So we're taking three vectors, triple product, and then it's called the scalar triple product because it's trying to remind you that it should be just number triple product, I guess. But scalar triple product sounds much more sophisticated, and what they mean is from three vectors they're creating a scalar or a number. That number will happen to be, why did we give a definition? Well, it's probably important or connected somewhere, and yes, it will be the volume of these parallelepipeds in absolute value. If you have right hand rule, it's the volume. If you have left hand rule, it's the negative of that volume. And we've got absolute value and determinant and norm and some symbol problems, notation problems, but you'll see in a second. Let's do a theorem. All right, for the three-dimensional analog, the word of the day is parallelepiped. This is going to be a box, essentially, which doesn't have necessarily 90-degree angles, so it's been pushed on slightly. It's going to be, again, determined by u and v and w. We're going to use a little bit of trigonometry again, but what we're pointing out is theorem. The scalar triple product of three non-coplanar vectors is the volume of the parallelepiped formed by u and v and w. Say parallelepiped 3 times fast. The scalar triple product will be the volume if they form a right-hand triple, and it'll be negative of the volume if we get a left-hand triple. Basically, this is saying you have to take the absolute value at the end. Volume is positive, so even in this calculation, if you get a negative, the volume will be the absolute value of that. And then this is the quick derivation or the justification as to why this volume works this way. U dot v cross w by definition of dot product is norm of u times the norm of v cross w times cosine of the angle between them. But if you use some trigonometry in this picture right here, this guy, u cos theta, is in fact the height h here. And then this right here is the area of the parallelogram determined by v and w. So this thing right here is, we know that by definition, oh, see, I was copying from Mark's notes. When you copy, your notation gets in there. When you're copying your homework, make sure they all go into the new notation, otherwise, gotcha! So Mark uses ABC, I used UVW. So when I have this, we know that the norm of v cross w was one of our conditions. It has to be the area of the parallelogram determined by u and or v and w, and this guy using trigonometry is exactly the height. The volume of a parallelepiped is the height times the base parallelogram, and so that gives us exactly, the moral of the story is the volume of the parallelepiped is the scalar triple product. Let's do one example, and how do we compute scalar triple product? All we're going to cleverly do is put u in the top row instead of ijk, and then compute a 3x3 determinant. Yes. All right, coincidentally, this is what we saved. I know you're very nice. She saved it till the end. She didn't want to see any of the angular momentum business. She wanted to see, like, how do you compute volumes of parallelepipeds when I've got coordinates of vectors and the numbers are back in there. So Alice is back. She's going to pay attention. You're just going to half fall asleep like the students, aren't you? Okay. So I have three vectors. They have coordinates in some canonical basis of 3 space, I, j, k. U, v, and w are the vectors I'm given. I want to know what the volume of the parallelepiped determined by these vectors are. Coincidentally, if I compute this scalar triple product and it's 0, what does that tell me? There was no volume. The volume was 0 is what it just told me. The volume is 0, what does that mean geometrically? All three vectors are coplanar. One of the vectors isn't sticking out and there is no box, and therefore there's no volume. So this is a way that Mark also likes to give you questions about. Determine whether these vectors are a basis of 3 space. Any three non-coplanar vectors are a basis for 3 space. So as long as their scalar triple product is not 0, then they're non-coplanar. If and only if, right? You're making this, are you comfortable? at least one of us is comfortable. All right, how do I do this? What we know now is the volume of the parallelepiped determined by these three vectors is equal to, I know, it's very exciting, isn't it? You need to watch upside down. Okay. You can do whatever you want when it's COVID. This is going to be U dot product V cross W, the scalar triple product. And then how do we actually compute this? It turns out, I'm going to chew the buttons. Why do you chew my buttons? Chew the buttons then. The cat tries to nurse me while I'm trying to give videos. What I do is I put the coordinates of U where I, J, K go. So I put U in the first row, 1, and then we put V in the next row, 0, 1, 3, and then I put W in the last row, 0, 1, 2. This is now going to be the volume up to the absolute value. What I need to know now is, though, be careful, I have a 3 by 3 determinant. I can cofactor expand along. I guess for cross product, I always have to use IJK to get it right. But I can cofactor expand along any row or any column. Because I have 2 zeros already, I'm going to choose to do this. So this determinant is equal to -1 times the cofactor C11 and then plus 0, 0. I don't care about the other two. So this is going to be 1, 3, 1, 2. So this is -1 times 2 minus 3, which is -1 times -1, which is 1. So the volume is actually 1. I don't know what it is. You have to go back to physics, units cubed. Whatever units you were, volume. So this is the efficient way of computing. The moral of the story is, oh, and one last thing I will sneak in there. If you have a pyramid or a prism is 1/6. You can stack 6 of these things inside the parallelepiped. So the volume of a pyramid is 1/6 the volume of the parallelepiped. Syncopated algebra. And then, of course, this is going to be 1/6 U1, U2, U3, V1, V2, V3, W1, W2, W3. So again, the moral of the story is also scalar triple product. You put the first vector where IJK was in either case. If you're going to compute volumes of pyramids or volumes of parallelepipeds using the scale triple product, which is the 3 by 3 determinant. If you're computing areas of parallelograms or areas of triangles, you're computing the norm of a cross product, which will be a 3 by 3 determinant with IJK in the top row. Either way, to compute areas and volumes in 3 space, we're using scalar triple product or 3 by 3 determinants. I'll see you next time. Please subscribe right here and like the kitties.